two users hit your checkout endpoint at the same millisecond, and one of them sees a bank balance that never actually existed. That's not a bug in your code, it's your transaction isolation level quietly betraying you. Today we're going deep on what isolation levels actually do, with real side-by-side SQL sessions so you can see the failures happen live. Isolation is the I in ACID, and it answers one question: how much of another transaction's in-progress work can you see? The SQL standard defines 4 levels, each trading correctness for speed. We'll build up from the leakiest to the strictest, breaking something new at each stage. Read Uncommitted lets you see rows another transaction hasn't even committed yet. If that transaction rolls back, you just acted on data that never officially existed. That's a dirty read. Read Committed fixes that, you only ever see committed data. But run the same query twice inside one transaction, and it can return different results if someone else commits in between. That's a non-repeatable read. Repeatable read locks in a consistent snapshot for your whole transaction, so that specific row can't change under you. But new rows matching your where clause can still appear. That's a phantom read. Serializable is the strictest level. Transactions behave as if they ran one after another, no interleaving at all. You get full correctness, but the database enforces it by aborting one of the conflicting transactions with a serialization failure. Let's actually run the dirty read scenario in 2 real PSQL terminals so you see the mechanics, not just theory. Notice we have to explicitly set the isolation level, because most databases don't default to read uncommitted anymore. Fun fact, Postgres doesn't actually implement true read uncommitted, it silently upgrades it to read committed. So on Postgres you won't see dirty reads at all, but on MySQL's InnoDB with that isolation level explicitly set, you absolutely will. This is why it works on my database, Bytes teams during migrations. Now the non-repeatable read, live. Session B reads a value, Session A commits a change, and Session B's second read inside the same transaction sees the new value under read committed. So how does Postgres give you a consistent snapshot in repeatable read without locking every row you read? The answer is MVCC, multi-version concurrency control. Every row keeps hidden version metadata, and each transaction sees the version that existed when its snapshot was taken, so readers never block writers. MVCC solves reads, but writers can still collide, so you need explicit locking for read-modify-write logic like decrementing stop. Select for update locks the row so a second transaction has to wait instead of racing you. Here's the real trade-off: stricter isolation means more serialization failures and retries, which costs throughput under high concurrency. Looser isolation means more anomalies your application has to tolerate or ignore. There's no free lunch, you're choosing where the pain shows up. Different databases default to different levels. Postgres and Oracle default to read committed, MySQL's InnoDB defaults to repeatable read. If you're moving workloads between engines, this single setting can silently change your application's correctness guarantees. Practical rule of thumb: use read committed for most everyday CRUD work, reach for repeatable read or select for update when you're doing read then write logic like inventory or balances, and only pay for serializable when correctness genuinely can't tolerate any anomaly, like financial ledgers. Isolation levels aren't just a checkbox, they're a contract about what bugs you're willing to accept, so pick one on purpose instead of inheriting the default.